Hey guys, welcome to 12.3. All right, today we're going to talk about tangent lines and velocity. And way back in chapter 1, we talked about average rate of change, which is essentially slope, right, of the secant line between 2 points. So if I look at the pictures down here, I've got my first point right here, and it's the point x, f of x. And then I got my second point right here, and to get that point, I added h to my x value, which means I have x plus h and f of x plus h. So if I want to talk about the slope, it's going to be change in y over change in x, which is going to be my f of x plus h minus f of x over h. And then what happens, you'll notice as I go through these drawings, that h gets smaller and smaller and smaller until it disappears altogether, because my 2 points are getting closer and closer and closer together until all of a sudden my 2 points are the same point. So now I can find the slope at that single point, which is now a tangent line. And in order to do that, I use this formula down here, which is that my slope, m, is the limit as h approaches 0 of my difference quotient, which I hope you remember from chapter 1, but that's basically the change in y over the change in x when the change in x has gone to 0. Okay, so in example 1 here, we need to find the slope of the line tangent to the graph y equals x squared at the point 2, 5. So first what we're going to do is we're just going to find the general slope, and then we're going to get specific to what happens at the point 2, 5. So in order to find the general slope, we go ahead and we use our formula from above, which was my slope is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. All right, so I'm going to find these separately. So I'm going to find f of x plus h first. So I'm going to go ahead and I'm going to plug x plus h in for x in my formula. So I get x plus x squared plus 1. And then I'm going to go ahead and multiply that all out. So I get x squared plus 2xh plus h squared plus 1. And then I'm going to do f of x plus h minus f of x. So I'm going to take everything that I just found. So x squared plus 2xh plus h squared plus 1, and I'm going to subtract x squared plus 1, which is my f of x. I'm going to put all of that over h, and then again, this is the limit as h approaches 0. So basically what happens is my x squareds cancel, because x squared minus x squared, my 1's cancel, 1 minus 1, and then I'm left with the limit as h approaches 0 of 2xh plus h squared over h. And then when I simplify that, actually my h's cancel out, and I am just left with 2x plus h, right? Because this h cancels out that h, and it cancels out one of those h's. So as h goes to 0, so this guy goes to 0, I basically plug in 0. That's what we do with limits, right? I find out that the general equation of my slope is 2x. But my equation of the slope at the point 2, 5, I have to plug in 2 for x, and I find out that my slope is 4. And that's my answer to the slope of the line tangent to the graph at that point. So example 2 is only slightly different because now it wants me to find it at any point. So basically I'm just doing the first part of what I did above, and then I don't even have to plug in any x values. So again, I'm going to start by finding f of x plus h. So I'm going to plug in x plus h into my equation, into my function for x, and then I'm going to multiply it all out. So x squared plus 2xh plus h squared plus 2, and then I'm going to take that and I'm going to subtract the f of x. So now I'm going to find the limit as h approaches 0 of x squared plus 2xh plus h squared plus 2 minus my x squared plus 2, which is my original function, all of that over h. And then again, a bunch of stuff's going to cancel. So essentially, most of the time, anything without an h in it cancels. And then my h's simplify, so this h cancels this h and one of those h's. So I am just left with 2x plus h. And then as h goes to 0, I am just left with 2x. And that is my equation for the slope of the line tangent to that graph at any point. And then once I'm given a specific point, I can go ahead and I can plug it in. Okay, so way back in chapter 1, we calculated average speed by picking 2 points along our curve and just finding the slope between those 2 points. And we're going to take that concept and we're just going to add dimension to it. So now we're going to talk about how we calculate average velocity, and then in just a second we're going to calculate instantaneous velocity. And average velocity is still change in distance over change in time, but now this time if we wind up with a negative, then we have to understand that basically we're talking about it's going down versus up. Okay, but my equation is still this equation right here, change in y over change in x, which is my slope formula. So for example 3, we've got this physics experiment. They're catapulting a ball upward. The height of the ball is represented by that quadratic, and t is time in seconds, and the height of the ball is measured in feet. And we want to find the ball's average velocity between time 1 and time 2. So basically we need to find, oops, don't think I want to be in highlighter mode. Let's try that again. So we want to find the height of 1 second, and we want to find the height at 2 seconds, and then basically we're going to plug them into our formula. So I'm going to plug 1 in, and that winds up being, let me see, I think 94. And then I'm going to plug 2 in, and that winds up being 141. And then I'm going to apply the formula above. So change in y, so 141 minus 94 over 2 minus 1, which winds up being 47. And then my y value is measured in feet, and my x value is measured in seconds, so it is 47 feet per second. And that is my average velocity. So in the example above, that tells me how fast the ball was traveling on average over the course of 1 second. But if I want to know how fast it's going right now, then that is my instantaneous velocity. And then that's where we start to take our difference quotient into effect and do the limit as h approaches 0, because that will tell me instantaneously how fast the object is going. And basically how fast it's going is the slope of the tangent line. Spoiler alert. So let's talk about tourism, because why not? So tourists standing on a 300-foot tall viewing tower drop coins in the fountain below. The height of the coin falling after t seconds is given by this quadratic function. Find the instantaneous velocity of the coin at 2 seconds. All right, so this word instantaneous tells us that we are going to use our formula for instantaneous velocity, which is the difference quotient, but with the limit applied to it. So the first thing I'm going to do is I'm going to go ahead and figure out what f of t plus h is. And so I'm going to plug in t plus h where there was t, and I'm going to go ahead and I'm going to simplify that equation. So 300, and then it'll be minus 16, and that'll be times t squared plus 2th plus h squared. And then I'm going to go ahead and I'm going to distribute that. And that's going to give me 300 minus 16t squared minus 32th minus 16h squared. So then I'm going to take all of that and I'm going to, for expediency's sake, right next to it, subtract the original function, which is 300 minus 16t squared, and I'm going to put that all over h, and it's going to be the limit of that as h approaches 0. And so once again, anything that doesn't have an h is probably going to cancel. And so all I'm left with is this part, and then this h cancels that h and one of those h's. So I have to find the limit as h approaches 0 of negative 32t minus 16h. But again, h is going to 0. So because this goes to 0, it's essentially negative 32t. So that is the slope of the line. That's the equation for the slope of the line tangent to it. But I need to know what happens at 2 seconds. So I'm going to go ahead and I'm going to plug in 2 for t. And I find out that my instantaneous velocity at that point is negative 64 feet per second. So right at 2 seconds, that is how fast the coin is falling. Okay, just to complicate the thing just a bit, let's talk about bees. So the distance a bumblebee flies along a path is given by this function. which is a cubic, because why not? Bees are complicated. T is given in seconds, and the distance of the bumblebee from a starting point is given in inches, and we need to find the equation for the instantaneous velocity of the bumblebee at any point in time, which means we're going to use our difference quotient. So I am going to find first P of T plus H. So I'm going to go ahead and I'm going to plug in T plus H anywhere there is a T in my original equation. And then I'm going to go ahead and simplify. And I think I'm going to get a little sneaky. And remember that we know how to do this because we know this is going to be 1331. So it's going to be t cubed plus 3 t squared h plus 3 th squared plus h cubed. Doesn't feel nice to know how to do that and not have to figure it out. All right, which means that we wind up with 12t plus 12h minus 6t cubed minus 18t squared h minus 18th squared minus 6h cubed plus 1. Whew, that was a lot. All right, and then we're going to go ahead and we're going to subtract our original function, which is 12t minus 6t cubed plus 1, and all of that is going over h, and that's going to be the limit as h approaches 0, so just ignore that little equal sign right there because I'm too lazy to write it all over again. All right, let's cancel some stuff out. So my 12t's are going to cancel, and let me see, my 6t cubed, that's going to cancel, and my 1's going to cancel, still leaving me with a bunch of stuff. Let me see, so this h cancels that h, it cancels that h, it cancels one of those h's, and it cancels one of those h's, which leaves me with 2 h's. All right, so what we are left with is the limit as h approaches 0 of, and you got to be really careful to make sure that you're, as you go through, you get all the bits and pieces. So we've got a 12, we've got minus 18t squared, I got minus 18t, and one of those h's is still there, and then I have minus 6h squared. All right, and then, of course, h is going to 0, which means this goes to 0 and this goes to 0, so we are only left with my equation of my velocity, my instantaneous velocity, as 12 minus 18t squared. And that is my equation for the instantaneous velocity at any point in time. And then if I know a specific time, then I can go ahead and I can plug that in for t, and that will give me that. But for right now, this is my answer.